tow-TEM is a time-domain electromagnetic system designed to be towed behind an all-terrain vehicle. tow-TEM has been developed over the past 3 years by the Hydrogeophysics Group at Aarhus University, led by Esben Auken. In October 2017, Esben came to California, worked with a group of us at Stanford and Aaron Fukuda from the Tulare Irrigation District in California's Central Valley to test the use of this tow-TEM system for assessing various locations as possible sites for on-farm recharge, also referred to as surface spreading. This is a view of one of the almond groves in which we worked. The question we had, what's below the ground? If we were to flood the grove, where is there clay underneath that would impede the downward movement of the water? Where are there permeable pathways of sand and gravel that would prevent ponding of the water at the surface and move the water downwards so as to recharge both shallow and deeper parts of the groundwater system? What we needed? An image of sediment texture beneath the almond grove. So we tested out using tow-TEM. The system was shipped from Denmark in the wooden crate shown here and put together at the field site in approximately 2 to 3 hours. The two main parts of the system, the large square frame is the transmitter. There is one loop of wire inside, 2 meters by 4 meters. This transmitter generates a magnetic field that travels down below the ground, inducing eddy currents that generate a secondary magnetic field measured by the receiver. That is the smaller unit, pulled behind the transmitter, with an offset between the two of 9.5 meters. The system is about 2 meters wide, so it fit perfectly between the rows of almond trees with their spacing of 6.8 meters, or about 22 feet. You can drive the system at 10 to 15 kilometers an hour, imaging to a depth of 50 to 80 meters below the ground surface. The depth to which you can image depends upon the electrical resistivity of the subsurface. So we were able to cover the almond field in about 5 hours. The slowest part in the whole process, as you'll see here, is turning at the end of the rows. There wasn't a great turning radius and we needed help getting the receiver into the next row. The next site we visited was this large recharge basin. What we were doing here was to see how well, again, we can map out what's below the ground surface. Where are there sands and gravels? Where are there clays that control the rate at which water will infiltrate into the ground? Here we are driving the system. Covering this recharge basin, we used a spacing between lines of 10 to 15 meters. And it's pretty easy to drive, as you'll see here. So in 2 days, we covered 1 almond field, 1 pistachio field, 1 open field, and 2 active recharge basins. Here is the resistivity model derived from the acquired data of the region beneath the ground in the almond grove and of a smaller region beneath an open field across the street. The displayed warm colors, red, are high resistivity units, such as sands and gravels. The cool colors, blues, are low resistivity units, or electrically conductive units, such as clays. We have the Google Earth image below just to display where the data were acquired, but the data that are shown here correspond to resistivity values below the ground surface. So the red zone you see is just below the ground surface, and we're typically seeing to a depth of about 60 meters. In this last image, we have transformed the resistivity values to sediment texture. So we are mapping out coarse-grained sand and gravel as orange, fine-grained clays are blue, and a small amount of mixed coarse and fine shown as green. The way the measurements are made, it is as if you are driving between the rows of almond trees and drilling a well every 15 meters and describing sediment texture down to a depth of 60 meters. The size of the vertical intervals, for which we can identify lithology, is about 1 meter at the surface, increasing to about 6 meters by the time we get to the total depth of 60 meters. We can see beneath the almond grove well-connected regions of sand and gravel, optimal for recharging the groundwater system. In contrast, there are areas in the field across the street where there are significant amounts of clay that could prevent rapid downward movement of the water, causing ponding at the surface. This information about sediment texture is exactly the information that we need to assess a recharge site. So tow-TEM was a complete success. We were able to obtain from our tow-TEM data images of what's beneath the ground surface, information that is critically important in assessing the suitability of a site as a location for on-farm recharge.